Good morning. This is your Stat Sensei, Mr. Spensei, and this is an exit ticket for the paired t-test. And our scenario is baked. A company bakes thousands of computer chips. That sounds like a population size. Each hour in two ovens, oven A and oven B. The chips are randomly assigned to an oven. All right, so we have random assignment. And hundreds of chips are baked each hour. The percentage of defective chips coming from these ovens for each hour of production through a day is shown below, and the distribution of the differences are normal. Okay, so we know we have normality, which is important because we have a small sample size. It's not going to be normal by central limit theorem because our sample size is not greater than 30. So based on the data, conduct a test in an alpha of 0.05 to determine whether oven B produces fewer chips than oven A. All right, so here's what they've done. This is tricky. Each hour, they have two measurements. All right, a measure for oven A, a measure for oven B. And they're making a comparison between the two. Because they're comparing at each hour, we have two measurements, one for each hour. This makes this paired, right? Because we have two measurements for each hour. So, first off, it's going to be a paired test. So I need to use T equals X bar D minus mu D SD divided by square root of N, which is essentially the same formula as we have for a regular t-test, except with a regular t-test, we don't have the D's. And the D stands for the differences. So this would be 40 minus 36 gives me 9. And 32 minus 37 is negative 5. So I've gone ahead and I've entered that data into the calculator. And you can see it all listed right here in L1 and L2. But what I want is the differences. So I'm going to go to the top of L3 and I'm going to go blue 1 minus blue 2. And there's my 9, negative 5 all the way down. So at this point, I can go do a stat calc, one variable statistic, stat calc, one variable statistics, and I blue 3 because I need column L3. And I find out that I get a sample mean difference of 1.1 with a standard deviation of 4.28. So on average, it looks like oven A is going to have about one defect, 1% more defects than the oven B. So here we go, 1.11, and this is our number of pairs. And in this case, we have 9 pairs and our sample standard deviation of 4.284. All right. We know it's going to be a one sample. This is a T, so it's a one sample T, but we need to specifically add the word paired. So super important that you don't just say one sample T test. If it's paired, please include the fact that it's paired. All right. All hypothesis tests are centered on the mean, the population mean. Confidence intervals are centered on X bar. And I also should make a note that when we're working with paired, we're assuming that there is no difference, that oven A and oven B are equal. That's the assumption. And if there's no difference, then it's like, oh, well, 45 minus 45 is 0. 32 minus 32 is 0. So we'd expect it to be 0. That's the claim. It turns out we ended up with an X bar of 1.111, and that's our X bar. And so we're shading up and to the right. Okay? And they want to see that if oven B has fewer. All right. So if I'm going to write oven A, I'm going to write A and B, and they're saying, hey, we expect A to have more than B, B to have fewer. It's like, oh, that's less n. That's where that came from. So now I need to plug in. Well, there's my sample mean, my X bar being plugged in for the 1.111. There's my population mean. Here's my sample standard deviation. And N9 is my number of pairs. Well, the claim is that it equals 0, that there's no difference. All right. So, and this will, and by the way, the null hypothesis will always be equal for this course. All right. And if it's paired, it'll always be 0. Please don't forget the D. Well, the alternative, so we have the ho and we have the ha. This part's the same. This part's the same. The only part that's different is right here, this inequality. This is the only thing that's different. And we just said, hey, we expect A to have more than B or B to have less than A. All right. So let's go ahead and run this test. So stat test t-test. If it's over here on stats, you need to move it over to data because we have our data list is in stat edit. We have a mean of 0. We don't care about L1 and L2. That's where this data is. What we care about is L3, so blue 3. And we said, oh, we need a greater than. And we end up getting a t-statistic of 0.7779. All right, with a p-value of 0.2295. So the probability that t is greater than, and by the way, just as a reminder, this matches this, which matches that, which matches this. All of those greater than signs need to match. Okay? So we have a p-value, or they gave us a, excuse me, not a p, our p-value is 0.2295, but they gave us an alpha up here of 0.05. So when we compare our p-value of 0.2295, we find that it is greater than our alpha. Could have been less than, but in this case, 2,295 is definitely greater than 500. So our decision is to fail to reject the null. All right, I appreciate you watching. Hope this helped and look forward to seeing you on the next one. Thank you.